Alright guys, welcome back to the channel, and today we're going to be talking about the Iris V2 dual deployment rocket, open rocket simulations, and you know what, let's not waste any more time here and let's just cut to the chase. Alright guys, so let's now dive into the open rocket simulation of the rocket and the design of it. So open rocket is like a CAD software used by many hobby rocket enthusiasts, and it really helps us because it's like a notebook. It has a lot of like custom components that we can design, like as from like the payload, which is like I named it, but like the airframe to your couplers. We'll dive all into that. It gives us like an idea of how high our rocket might go, or what's the maximum roll rate or the maximum velocity, as we can see with this number right here. So we can see a lot more than this, but we'll dive into that later. So let's just talk about the rocket and we'll go from the bottom to the top. So this is the apogee section we're going to be talking about. So let's start with the fins. So these are a 1/4 inch thick trapezoidal fins, and they're made out of aircraft plywood. So they're pretty decent in density. They're not way too dense, but they are thick for what they should be. So the goal of this rocket was to have a good stability margin to do dual deployment and just have a rocket built like a tank, right? So these 1/4 inch fins, plywood fins would work really well, as that goes along with the mission of this flight. And we use 4 fins as it gives us the maximum amount of stability. And then talking about stability, also I love these fins because you can see it follows the rule of thumb, which is that your center of gravity, which is the balance point of the rocket, as we can see here, and the center of pressure, which is the maximum aerodynamic load that will be applied on the rocket, they're about 3 inches away from each other and a little over that, which is good because the rule of thumb, which is that your airframe diameter must be the distance at least away from your center of pressure. So your CG must be ahead of it. So in this case, it should be ahead of it by at least 3 inches. So we can see that this is sufficiently meeting that requirement with these values right here, which is in the metric system, which we by default use. But you can change that, right? So what we can see, if we change certain values of this, we can see that the CP goes back a little, but these fins look really wonky, so we wouldn't want to do that. But we can see if we do that, it gets closer. But if we just go back to normal, which it resets and it looks is plenty far away. All right, so now let's just talk about what holds the motor. So this gray block is the motor, and we'll talk about the motor a little later. So the motor is held by this paper wound tube, which is really thick, or you can also consider it to be cardboard. So this holds the motor to by center rings to the airframe. So the airframe is 3 inches in diameter, and this is made out of the center rings are made out of wood and plywood, or just plywood in general, because what this really helps with is the strength of it, right? Printing out a PLA and PETG, you could have some unconformities, and what the problem could be is if there's like gaps or layers that are missing, that could make it much weaker. And when you have that motor ejection or your dual deployment rocket ejection, that the the anchor can be yanked away, which we do not want at all. So that is it. So that's it for this section. Now let's just talk about the recovery. So we utilize 10 feet long tubular nylon shock cord, as it's a little bit flame resistant, but also it is thick enough so it doesn't absorb much of the heat. But it does get a little crispy after a couple of flights, a pun intended, and it's 10 feet long. Doesn't have to be very long, as it's just our apogee section. And this is our 28-inch parachute, which is made out of ripstop nylon, which is good because if you're ejecting at a high velocity or have a high velocity descent, it won't rip very easily, which is very nice. Now moving on to the electronics section. We'll dive into this section much deeper, but from a vague standpoint, the electronics are held in this coupler, right? So the coupler holds these two pieces of the 3-inch airframe together. And then this is our electronics simulated. And then this is a switch band. So basically, if I wanted to access the screw switch, I don't have to get the electronics out of the rocket from the inside, but we can just access it from here. And the screw switch is what basically arms the rocket or turns it on. We'll get into that a little deeper later. So this is also a 28-inch main parachute. This is now our main section we're talking about. And I will talk about how this backfired on me, which is pretty sad. Um, Moving on, then we have a Kevlar 16 feet worth of Kevlar, and basically Kevlar is great as I bought this custom because this is where the higher amount of grams should be for your black powder charges. I since I did use the same parachute like size, I didn't need to increase the grammage of the black powder, but I just wanted to make sure that this lasted longer and I didn't have a lot of Kevlar left, I decided to use 16 feet of 12 strand 3/8 inch Kevlar, which is decently thick. And then we have a polycarbonate nose cone. All right, so going back to the lower section of the rocket, so the motor is going to be held together through this Z clip retention. So basically, you have two screws at the end of the rocket, and that holds the motor together, which is really nice because I don't have to use tape, which can wear out the cardboard piece that sticks out of here, the motor liner tubing. So that is really crucial. So that's why we utilize Z clip retention. So now let's just dive into the simulations. All right, so before we dive into the simulations, and in order for that to work, we actually have to talk about the motor configuration. So, what motor configuration is like basically where you choose your motor, which is really fun. So, I decided to use a Aerotech H130-6. So, what this indicates is that it has at least 130 Newton seconds worth of average thrust, and this is a White Thunder motor, so it's really loud and it has a dash six ejection delay. So after 6 seconds, the ejection charge will fire. And wait a minute, before I did say that you shouldn't be using motor eject, but that's only for high performance. And this since this is my first dual deployment test flight, I decided to just have it because it would just serve as an extra backup if both of these charges here didn't fire. So that would be nice. So like just going into it, Open Rocket's really nice, gives us a whole selection of motors. So I chose the high powered category as it would be good enough to get the rocket off the pad into a decent altitude above 1,000 feet. And then we can see the details of this motor. So we see the common name of it. The average thrust is 135 newtons, but 130 is your motor designation. So your average thrust is also right here. You can get a close estimation from that. But the actual average thrust is 135 newtons. Max thrust, all of this is in newtons and seconds, and launch mass in grammage. So that's how much it will weigh with the whole liner casing. So this is a reloadable motor. So I have a special liner for this, and basically I have to assemble the motor with the given pieces. And then the lightning is really loud, as I mentioned before. And then we can see this thrust curve here that shows like the whole burn profile of it, which is really cool. There's much more better ways you can see this, but Open Rocket just gives you a very like good estimation of how it should look like. So now we can move into the flight simulation. So we have multiple flights here, as you can see, and we can run the simulation. So we can see it's actually running, compiling the values. So both of these say that it's going to reach 1,211 feet maximum. So really, these both have something in difference. So that's actually their ejection charge delay. So what's nice about Open Rocket was before you start experimenting with this, you should also look at the optimum delay. So that's how we got the 6 second value here. It tells you what delay should you use before you reach apogee. But in my actual flight, I did resort to a H130-10 all of a sudden because I wanted to be a little after the apogee charges fired from the rocket because I wanted to see that individually happen first before we did the motor eject. So we'll just delete the simulation right here. So we can see the whole flight time, ground hit velocity, and now we can actually plot this in a chart. So we can show what we want, the altitude. I have a lot of things I could put here, but just for the sake of simplicity, we'll just put the altitude, vertical velocity. And look, there's a lot of things that we can change. So we can see all of this and then vertical acceleration. So this is just vertical motion over time. And we can export this data as like a CSV file. And all this is a metric system. So I'm sorry. Besides this, actually, the altitude in feet, it's easier on the eyes. And I don't have to convert it all the time. And then what's really nice about Open Rocket on the day of launch, if you really are that tedious and wanting to do it, you could put the average wind speed and put this and get like a very, very close simulation to what it's going to be like in real life. So let's just simulate and plot this, and we can see all of this is just a lot of details, and we can just do this, and now we can plot the simulation. All right. All right, so we can see that the recovery, there's going to be two separations. So this is the apogee charge, right? Apogee charge, and then we have a recovery device deployment. So how I modeled these was, if I can go back in the motor configuration section, I was able to model these at different altitudes. So I said apogee this will happen at apogee, and this will happen at 500 feet. But the problem with this is it doesn't show the motor ejection charge, but we can get a close up approximation. It'll be around here. So this shows your whole ignition status, burnout, and then recovery device deployment. It shows you the vertical velocity, all of these velocity measurements all over here. And to be honest, they were surprisingly close when I did the actual flight. So we can also export this image, and that's really nice of OpenRocket. And then we can see when it hits the ground, and we can zoom in on these values. So one thing it's crucial to know about OpenRocket is that you see how these lines are a little dashed and a little away from each other, these dots. So basically that like signals that the parachute has come out, and this shows that the whole rocket is still integrated. Well, if you zoom in, it's going to be much further away, but the point is clear, right? That this shows that the parachute has deployed, and this is still showing that it's still burning and going up. So this was the open rocket diagram, or CAD design as you could say it. And what's also great about Open Rocket is that I can get a 3D finished model and I can see how it looks like. So I did forget to change the color of this to the actual color, but you can see I can change the color, which is really cool. So in reality, this wasn't a white airframe, it was a red. So we can change that in Open Rocket. So we just go here, and we can choose what type of color. Red, this looks pretty close. And then that's it. And then now we should have a pretty close representation of what the rocket looks like. So it looks pretty beautiful. The plywood is right here, and that's the whole nose cone right here. It looks beautiful. And then we can see the 3D figure, and this just shows all the components inside the rocket. And they can get the unfinished figure. It just shows how the rocket looks unfinished. So the plywood, all of that fun stuff, just the anatomy you could see of the rocket. So that's it for the open rocket section of this video. Now let's move on to the electronics of the video of how I did it. All right, guys, that's just a wrap up for today of the open rocket simulations we discussed here. So all in all, we basically discussed how I went through the design process of making the rocket and why I chose certain components, and more importantly, we talked about the simulations of the rocket and all of that fun stuff. So let's not waste any time here. I got another video to upload for you guys. So see you in a bit.